All right, let's just jump right into it. You know, we are literally swimming in invisible information all day, every day. I'm talking about Wi-Fi, Bluetooth, our cell service, the whole shebang. And it feels like pure magic when it's working, right? But the second it doesn't, it is just maddening. Today, we're going to pull back that curtain and look at the fundamental physics that actually run our wireless world.
Oh, we have all been there. You're streaming a movie, it's crystal clear. Then you walk into the kitchen and bam, the buffering wheel of death. Or you're on a super important video call, everything's going great, and then suddenly your boss's face freezes into some kind of modern art sculpture. This isn't just random bad luck. There are real, physical reasons this happens, and by the end of this, you're going to understand exactly what they are.
So, to really get a grip on wireless, it actually helps to look at its older, much more reliable cousin, the good old wired connection. I mean, think about an Ethernet cord. It's basically a private, protected highway just for your data. It's consistent, it's isolated from all the chaos of the outside world, and it has a fixed capacity. You know what you're going to get. Wireless, though, that's a completely different beast. It's like a chaotic public square. It's unpredictable, it's full of potential errors, and its capacity can change from one second to the next. So, how in the world do we send information through this noisy, chaotic public space? Well, we have to use a language that can actually travel through the air itself. And that language, my friends, is built on waves. Okay, so at the very heart of everything is the signal. The easiest way to think about it is like a simple wave in a pond. And it has two really key properties. First is amplitude. That's just the height of the wave. Think of it as its strength or its volume. And second is frequency. That's how fast the wave is cycling up and down. That's what tells us how much information we can cram into it. Now, these signals really come in two main flavors. You've got analog, which is this smooth, continuous wave, kind of like the sound of my voice. But the signals our computers and phones use, those are digital. They're different. They use these blocky, distinct levels that represent ones and zeros. And here's the crucial part. While an analog signal can get totally messed up by a little bit of noise, a digital signal is way more robust. See, even if it gets a little bit distorted, the receiver can usually still figure out, oh, that was supposed to be a 1, or that was a 0, and then rebuild it perfectly. So the big question is, how do we get our digital ones and zeros to actually ride on one of these analog waves? Well, there's a process for that, and it's called modulation. It's actually a pretty simple three-step recipe. First, you start with a really basic, predictable wave. We call that the carrier wave. Then you take your data, that stream of ones and zeros you want to send, and finally, you modulate. You just alter the carrier wave. Maybe you make it taller or shorter, or faster or slower, in a specific pattern that encodes your digital information. It's literally like using a flashlight to send Morse code across a field. Okay, so we're encoding data onto waves. That's great. But how do we make it go fast? This brings us to two of the most critical concepts in all of wireless: bandwidth and data rate. Let's go back to our highway analogy. Think of bandwidth as the number of lanes on that highway. It's the range of frequencies you're allowed to use for your signal. So, as you can see here, if our highway is, say, 4 megahertz wide, we can get a speed of about 2 megabits per second. Now, here's what's so cool about this. It's a really simple, direct relationship. If we double the width of our highway to 8 megahertz, guess what? We can double our speed to 4 megabits per second. It's a fundamental rule. More bandwidth gives you the potential for a higher data rate. More lanes, more traffic. Simple as that. But, you know, having a really wide highway isn't enough if that highway is filled with potholes, traffic jams, and other cars swerving into your lane. And in the wireless world, all that chaos is called noise. It is the invisible enemy of every single good connection. This quote right here just nails the problem perfectly. Your Wi-Fi signal isn't traveling down some nice, protected, private pipe. No, it's broadcasting out into the shared ether. That means it's competing with your neighbor's Wi-Fi, your Bluetooth speaker, even your microwave oven, basically anything that's using the same band of frequencies. It's like trying to have a quiet conversation in a ridiculously crowded, noisy room. So to figure out how clear our conversation is in that noisy room, we use a metric called the signal-to-noise ratio, or just SNR for short. And it is exactly what it sounds like. It's a simple comparison of how strong the signal you want to hear is versus how strong all that background noise you don't want to hear is. And trust me, a high SNR is the absolute key to a good connection. A high SNR, a great connection, looks just like this. The signal power is way, way stronger than the noise power. Your phone or your laptop has no trouble at all hearing the data being sent. The message comes through loud and clear. This is when your movie is streaming in perfect 4K. This is Wi-Fi nirvana. But then, you move too far from the router, or your neighbor fires up their brand new powerful Wi-Fi, and you get this. The noise power starts creeping up, and your signal power drops. Now your device is struggling. It can't easily tell the difference between the data and all that random noise, so it has to keep asking for the data to be sent again. That's buffering, or eventually it just gives up. That is your dropped connection.
So, given this constant, brutal battle against noise, how do engineers keep making things faster and faster? I mean, they can't just ignore the laws of physics, but what they can do is get incredibly clever at working within those laws. And one of the cleverest tricks they use is something called multi-level signaling. So instead of a really simple signal that just means 1 or 0, we can use much more complex signals. For instance, an 8-level system uses 8 totally distinct signal shapes. Now, each one of those shapes can represent 3 bits of data all at once. So as you can see in the table, that triples our data rate. But, and there's always a but, there's a trade-off. Those 8 levels are packed much closer together, which means you need a much cleaner, higher SNR signal for the receiver to tell them apart. You're basically trading robustness for more speed. So what's the absolute fastest we can possibly go? Well, let's imagine a perfect, theoretical world for a second, a world with 0 noise. In that perfect world, the Nyquist limit gives us the answer. The maximum capacity, C, is simply 2 times the bandwidth, B. So a 1 megahertz channel could, in theory, carry 2 megabits per second. But of course, we don't live in a noiseless world, do we? Which brings us to the real speed limit. And here it is. This is the big one. This formula from the absolute legend Claude Shannon tells us the true, unbreakable speed limit of any channel in the real world. And just look at what it's made of. There's B for bandwidth, that's the size of our highway. And there's SNR, our old friend, the signal-to-noise ratio, which tells us how clean and clear that highway is. This isn't a guideline, this is the law.
Okay, let's make this feel real. Let's stop talking theory and just plug in some numbers. Let's say we have 1 megahertz of bandwidth and a pretty good strong signal-to-noise ratio of 24 decibels, which just means our signal is about 251 times stronger than the noise. We run that through Shannon's formula, and the answer is 8 megabits per second. That's it. That is the absolute physical limit. No amount of fancy marketing or clever software can get you past that number under these conditions. All right, let's bring it all home. Now that we understand signals and bandwidth and that constant battle with noise and the ultimate laws of physics, we can finally diagnose why your Wi-Fi connection is so frustratingly fickle. So who are the usual suspects? Well, it's everything we just talked about. It could be a low SNR because maybe you're too far from the router or there's a thick brick wall blocking the signal. It could be interference. That's just noise from your neighbor's network shouting in that same shared ether. It could be limited bandwidths because everyone in your house is trying to stream a 4K movie at the exact same time on the same frequency highway. And finally, there's a weird one called multipath, where signals literally bounce off the walls and ceilings, arriving at your device at slightly different times and just creating a confusing, garbled echo. So the next time your Wi-Fi starts acting up, you'll know. It's not some weird tech voodoo, it's just physics. It's a constant, incredible engineering challenge. And it really leaves us with this one final thought. If all of our wireless communication is really just a conversation happening in an impossibly crowded, noisy room, isn't the real magic the fact that we can design systems that are able to pick out a single tiny whisper at all?